Okay, today our first goal will be to discuss completions of locally convex spaces. The notion of completion actually makes sense for any topological vector space that is not necessarily locally convex, and more generally it makes sense for any topological abelian group, and even more generally for any uniform space. But in our discussion of completions, we'll consider locally convex spaces only, and I'll tell you later why this restriction is reasonable. So let's start with the definition of a completion. So suppose that we have a locally convex space X. Then we define a completion of X is a pair X tilde and J consisting of a complete locally convex space X tilde. X tilde is a complete locally convex space, and J is a continuous linear map from X to X tilde, which has the following universal property, such that for every, so let's draw a picture, for every complete locally convex space Y, so this is X, this is Y, and this is X tilde. And for every continuous linear map phi from X to Y, there exists a unique continuous linear map from X tilde to Y such that the diagram commutes. A unique psi tilde such that the diagram commutes. Okay, we can easily say the same, give the same definition in slightly different terms. Let's introduce first some notation. We'll consider the category of complete locally convex spaces. So this is a full subcategory in the category of all locally convex spaces, a full subcategory consisting of complete locally convex spaces. Then there is an equivalent definition of a completion, namely a completion of a locally convex space X is a complete locally convex space X tilde together with a natural isomorphism, between the set of continuous linear operators from X to Y and the set of continuous linear operators from X tilde to Y, where Y is a complete locally convex space. So natural means that this is an isomorphism of functors in the second variable. It's a simple exercise to show that these two definitions are equivalent. Just a standard category theoretic argument shows that they are equivalent. And any of these definitions readily implies that if a completion exists, then it is unique in the following sense. Let's just draw a picture. If we have two completions, say X tilde and X hat of the same locally convex space X, so suppose these are This is J, and K is the respective map for the second completion. So if we have two completions of the same space X, then there is a unique topological isomorphism between X tilde and X hat, such that the diagram commutes. This readily follows from the definition. Okay, how about the existence of a completion? The first step in proving the existence is to reduce everything to the Hausdorff, to the case of Hausdorff spaces. So let's introduce some more notation. If we have a locally convex space X, let XH denote the quotient of X modulo the closure of 0. And let pi h denote the respective quotient map from X to XH. XH is Hausdorff. Let's recall that the quotient of any locally convex space by closed subspace is Hausdorff. So it is Hausdorff, and it is called the Hausdorff space associated to X. XH is the Hausdorff locally convex space associated to X. And it's a simple observation that this space XH has the following obvious universal property. So let's observe that if we have a continuous linear map from X to a Hausdorff locally convex space Y, then this map uniquely factorizes through XH. That is, there exists a unique continuous linear map phi h from here to here, such that the diagram commutes. This is just a special case of the universal property of quotients, because since Y is Hausdorff, phi automatically vanishes on the closure of 0. And so we can factorize it through the quotient. So in other words, we have a natural isomorphism between the set of continuous linear operators from X to Y and the set of continuous linear operators from XH to Y for every Hausdorff locally convex space Y. So this is our first observation. And the second observation essentially means that if we want to construct a completion of X, it suffices to construct a completion of XH. More exactly, if we have a complete locally convex space X tilde and a continuous linear map J from XH to X tilde. So this is XH, X tilde, J, and here we have the quotient map pi h. So the observation is that J and X tilde form a completion of XH. So this pair is a completion of the Hausdorff space XH, if and only if the same space X tilde together with the composition of these maps, J and pi h, is a completion of f of X. Now this is basically just a simple observation based on this diagram. You will have a continuous linear map from X to Y, where Y is a complete locally convex space. So Y is complete, in particular it is Hausdorff. So we can first factorize this map through XH and get a map from XH to Y. And then if X tilde is a completion of XH, we may further extend this map to X tilde as follows, again uniquely. And this shows that the same space X tilde together with this composition is a completion of X. And the other way around. So this is a completion of x if and only if this is a completion of xh. As a result, we see that if we want to construct a completion, we have to do this only in the case where our space is Hausdorff. In the case where our space is Hausdorff, we can give an alternative approach to completions based on the following proposition, which is basically a special case of the extension by continuity theorem from the previous lecture. Namely, if x is a Hausdorff, locally convex space, x tilde is a complete locally convex space, and J is a topologically injective continuous linear map from X to X tilde. That is a topological embedding, such that its image J of X is dense in X tilde. Then X tilde together with J is a completion of X. And the proof is immediate from the extension by continuity theorem. Because since J is topologically injective with dense image, we can just assume that X is a dense subspace in X tilde and apply the extension by continuity theorem. So as a result, if we want to construct a completion of X, where X is assumed to be Hausdorff, we have to construct X tilde and J with all these properties. Okay, let's now turn to construction of the completion. Construction of X tilde. The construction will be based on the simple fact that every Norrand space has a completion, and I'm assuming you know this fact from your functional analysis course. By the way, before we construct X tilde, let me make a short remark here. So a corollary of this proposition. Namely, if X is a Norrand space, and X tilde is a completion of X in the class of Norrand spaces, X tilde is a completion of X in the class of Norrand spaces, that is in the sense of classical functional analysis, then the same space together with the same map J is a completion of X in the class of locally convex spaces. X tilde is a completion of X, well, in the sense of our definition. This easily follows from this proposition. Okay, so let's now construct a completion. We assume that X is a Hausdorff locally convex space, and we choose a defining directed family of seminorms on X. For every seminorm P in this family, who may consider the respective seminorm space XP, this is just the same space X, equipped with a single seminorm P. This is a seminorm space. And then let's make it into a norm space as follows. So let XP0 denote the quotient of xp modulo the subspace where p vanishes. And this is a norm space for the quotient norm p hat of the seminorm p. Or equivalently, this can be described as the Hausdorff space associated to xp. So this is a norm space. And since we know that every norm space has a completion, we may take this completion, let's denote it by xp tilde. So this is the completion of xp0. And this is a Banach space. This is a Banach space. So for every p in our family, we have the following picture. So we have the quotient map, let's denote it by p. This is the quotient map of x to xp0. And xp0 is a dense subspace in its completion, xp tilde. So the composition of these maps will be denoted by phi p. Let's now show that the Banach spaces xp tilde actually form a projective system. Well, indeed, you have two seminorms in our family P. So suppose we have two seminorms P and Q in our family, and suppose that P is dominated by Q. That is, P is less than or equal to a constant times Q. This implies that the subspace where Q vanishes is contained in the subspace where P vanishes, obviously. And so by taking the respective quotients, we see that there is a well-defined linear map, let's denote it by pi pq, which acts from xq0 to xp0. So between these quotients, which takes every element in this quotient represented by x to the element represented by the same element x. So this map is well defined because of this inclusion. It is obviously linear, and it is obviously continuous. Pi pq is a continuous linear map. Well, indeed, the continuity follows from this assumption. So it is bounded as a map between norm spaces because of this inequality. P is less than or equal to a constant times q. So it is a continuous linear map. And we have the following picture. This is x. This is xp0. This is xq0. Here we have the quotient maps pi p and pi q. And this is our map pi pq. So the diagram is obviously commutative just by construction. Now xp0 is contained in the respective completion, xp tilde. And similarly, xq0 is contained in xq tilde. So this composition is phi p, and this composition is phi q. And since pi pq is a continuous linear map between norm spaces, we can uniquely extend it to the completions, and we get a unique continuous linear map phi pq such that this diagram is commutative. To show that the Banach spaces xp tilde together with these maps phi pq form a projective system, we have to show that these maps phi pq are compatible, and this is very easy. Well, indeed, if we have three seminorms, p, q, and r, p is dominated by q, and q is dominated by r, so three seminorms in the same family, then it follows from the construction that pi pq, the composition of pi pq and pi qr, is just pi pr. just because of this construction. Since these spaces are dense in their completions, it follows that the same equality holds for the respective maps between the completions, and as a result, phi pq, phi qr, well, this composition is equal to phi pr. And this means exactly that the Banach spaces x p tilde, together with the maps phi pq, so they form a projective system. This is a projective system of Banach spaces. And moreover, by looking at this picture, we see that X, together with the family of maps phi p, becomes a cone, a projective cone. X, together with the maps phi p, is a projective cone over this system. Okay, let's now take the projective limit. Let's denote the projective limit by x tilde. And for every p, so let's recall that the projective limit is a kind of a universal projective cone over this system. So we have canonical maps psi p from x tilde to xp, the canonical maps. And since x is a projective cone over our system, then simply by the definition of a projective limit, we have a unique continuous linear map, J, from x to x tilde, such that the respective diagram commutes. So this is our map J. Here we have a phi p. Here we have psi p. So this diagram commutes for every p, for every seminorm p in our family. And I claim that what we have just constructed, x tilde together with j, is indeed a completion of x. This is our theorem. X tilde together with j is a completion of x. Well, obviously x tilde is complete because it is a projective limit of complete spaces. We know that because the completeness is preserved under projective limits. So by this proposition, we have to show that the conditions of these propositions this proposition are satisfied. So we have to show that J is topologically injective and has dense image. The proof, well, it's convenient to divide the proof into two lemmas. Lemma 1 is mostly a simple observation. Namely, if we have two locally convex spaces x and y, an injective linear map, continuous linear map J from x to y, an injective linear map, and a defining family of seminorms P, a defining family of seminorms on Y. Then I claim that J is topologically injective, if and only if the following family, consisting of compositions of seminorms from P with the map J, so this is obviously a family of seminorms on X, and J is topologically injective if and only if the family is defining for X. This is a defining family of seminorms on X. Well, the proof is a simple exercise. Actually, it is almost trivial, just by the definition of the induced topology. lemma 2 is also rather simple. Actually, well, we'll state it in the setting of topological vector spaces, but actually it can be easily generalized to arbitrary topological spaces. Namely, if we have a projective system of topological vector spaces, xi together with the maps phi ij, let x denote the projective limit of this system, and phi I, let phi I denote the canonical maps from x to xi. And let's also suppose that we have a vector subspace y in X, vector subspace. And for every I, I'll let yi denote the image of y in xi. So this is a subspace in xi. Then I claim that, first of all, the closures of these subspaces yi form a projective system. So we may consider the restrictions of phi ij to the respective closures. And this data is actually a projective system of topological vector spaces. And the projective limit of this system is nothing but the closure of y in X. The closure of y is the projective limit of this system. Well, actually, I've already included this lemma as an exercise in the respective exercise sheet. But because of its importance, probably let's try to prove it now. Well, the first statement is a simple exercise. Just use the definition of projective system. So first of all, observe that this is true without the closures. That phi ij takes yj to yi, and by continuity, it also takes the closure of yj to the closure of yi. This is trivial. So let's turn to the second statement. First of all, let's recall that the projective limit can be identified in a standard way with a subspace in the product. This is rather useful in this context. So let's recall that X can be identified with the set of those elements xi in the product of the spaces xi, which are compatible in the sense that every xi is equal to phi ij of xj whenever I is less than or equal to j. This is just our explicit construction of the projective limit. And of course, the same is true for the projective limit of the family of the system of the closures of yi. The only difference is that now we require that the respective elements xi sit in the closures of yi. So in other words, the projective limit of the family of the system y of the closures of yi consists of those elements in X for which every coordinate xi sits in the closure of yi for every I. And by the way, let's also recall that under this identification, the canonical map phi I is simply the projection onto the ith coordinate. Phi I of x equals xi for every I. So by looking at this equality, we see that this is nothing but the intersection of the preimages of the closures of yi. This is just another way of writing the same formula. And clearly this contains y. this contains y, just by the definition of yi. But since this is closed, well, the intersection of closed sets is closed. So it is closed, so it automatically contains the closure of y. So we have this inclusion. We see that the closure of y is contained in this projective limit. And now we have to show the opposite inclusion. Well, let's take an element in the projective limit. Say x belongs to the projective limit of yi. So we identified with the intersection of the preimages of the closures of yi. And we have the following little sub-exercise in the proof. So if so suppose that for every I, we have a base beta I of neighborhoods of 0 in xi. Is a base of neighborhoods of 0 in xi for every I. Then I claim that the following family of subsets, the family of their preimages under the maps phi I. So here I runs over